So we're going to talk today about the nuclear decay. Our learning target is to compare and contrast the different types of radioactive decay, and the success criteria that we need to be able to do to hit that learning target is to understand radio decay results in the emission of, okay? This radioactive decay gives off, it can give off an alpha particle, and we'll talk a little bit more in depth about what that is. It can give off a beta particle, we'll talk about that also. And finally, it can give off a gamma ray. So when we have radioactive decay, one of these three things are given off. We need to be able to identify the process occurring in the nuclear reaction when we see it written out in a symbolic form. So there's going to be a nuclear reaction equation. You need to be able to look at that and say, oh yeah, that's beta decay. So you need to be able to identify these four: alpha decay, beta decay, electron capture, and finally, positron emission. Most isotopes that are naturally occurring are stable. So most isotopes are stable. A few naturally occurring isotopes and all of the man-made isotopes are unstable. Unstable isotopes become stable by releasing different particles, and that process is called radioactive decay. And the elements which undergo the process are called radioisotopes. I've also heard it called radionucleotides, but, okay, most of the time I'm going to refer to those as radioisotopes, okay? So basically what we're saying here, okay, is that we have some isotopes that are unstable. And these isotopes undergo radioactive decay to reach the stability. And you're going to see that that's going to be occurring in the nucleus. So we're going to be dealing with changing the protons and changing the neutrons. Radioactive decay results in the emission of either, and we just talked about this in our success criteria, okay? An alpha particle, a beta particle, or a gamma ray. So, in alpha decay, the very first of these types of decay that we're going to talk about, an alpha particle that is identical to that of a helium nucleus is emitted. So, I just said there, this alpha particle, it's identical to a helium nucleus. Well, if we look at helium, okay, helium here has 2 protons. Helium has 2 neutrons. So what is going to be the atomic number for helium? Well, in order to have helium, the atomic number's got to be 2, right? In order to have this, what is the atomic mass going to be of helium? Well, 1, 2, 3, 4. So this is 4, 2 helium. So helium 4 contains 2 protons, contains 2 neutrons. So here is our basic equation. What I need you to do is make sure that you have this equation somewhere in your notes for alpha decay, because this is going to be very helpful to us tomorrow. So make sure that you write this equation for alpha decay in your notes. Now notice, right here is that helium-4. Okay, the atomic mass is 4. The atomic number is 2, and there's helium. This, ladies and gentlemen, this right here is your alpha particle that is being emitted. So what we're looking at here is this right here, this XAZ. This would be the unstable radioisotope. This would be, the Y here would be the stable radioisotope, and the He is the alpha particle that is given off in order for that stability to occur. So this is what is going on during alpha decay. I'm going to show you what this A minus 4, Z minus 2, okay? We know that. This is A is the number of nucleons, right? What was a nucleon? Who can tell me what a nucleon is? Jaden? It's proton and neutron together. Yes. Okay, so nucleon was proton and neutron together. Z is the atomic number. So what we're going to do here is we're going to take that number of nucleons and subtract 4. We're going to take that number of the atomic number and subtract 2. Why 2 and 4? Because that's giving us our helium right there. That's giving us our alpha particle. So like I said here, the unstable atom, the more stable atom, and once again, the alpha particle. If I look right here, Ra, which is radon. Okay. Ra, which is, actually it's radium, it's not radon, it's radium. So I've got radium right here, radium-226. This is my unstable isotope. So basically what's going to happen is it's going to split into radon-222 and helium-4. So the unstable is right here, the radium. The more stable is the radon and my alpha particle. When I put that into my equation form here, when I put that into my equation form, I take the radium-226, 88. What's 226 minus 4? 222. 88 minus 2 is 86. So there I can see that element number 86 on my periodic table is radon, because we'll have to do that later. And there's my helium. There's my helium-4, which is my alpha particle. So if you look here, the top numbers here on the right side of the arrow are equal to the top number on the left, correct? Correct? Yes. The bottom number on the left of the arrow is equal to the sum of the bottom numbers on the right. So this makes sense, mathematical, and it's easy math. Let's look at this right here, okay? Right now, we just made that radon, 222.86. We're going to look at that now, and we're going to make this into an even more stable. So, can we do the math and figure out what Y is? Okay? Well, the big thing to figure out, what's the biggest part of figuring out what Y is? How are we going to determine what element Y is? The atomic number, the Z, right? Right here. So we know that if we have alpha decay, we're taking this 86 and we're subtracting 2, right? What's 86 minus 2? Very good. It's 84. What is element number 84? Polonium. Okay? So you might want to take out your periodic table so we can see these different elements. So it's going to be polonium. Which isotope of polonium is it going to be? Well, we're going to need to look then what A is going to be to know what isotope of polonium it is. Okay? What is 222 minus 4? 218. So what I'm going to have for Y here is going to be polonium, PO. My A is going to be 218. My Z is going to be 84. So there we have it. We have just figured out this alpha decay problem. Wasn't too tough, was it? Now let's go the other way. Okay? Let's go the other way. I've been given my alpha particle. I've been given my more stable, which is TH. Let me find TH. I think it's thorium, but let me find him. Yep, it is thorium, element number 90 there. So what is my X? What is my unstable element here? Well, I am working backwards here. So what is my Z going to be right here, Zoe? It's going to be the atomic number. Give me the exact number. It's going to be 92, because remember, these on the right, 90 and 2, must equal what's on the left. What is element number 92, Zoe? Uranium. Now we need to figure out which uranium we have. Okay? Well, I can see, based on my math, 230 and 4 is what, Nick? 234. So this is going to be uranium 234. Now, believe me, folks, these get tougher when we throw all 4 of them together and you have to identify them. Okay? They get tougher when we put them all together. Well, let's start with our next one then. Our next one is beta decay. A beta particle is a fast-moving electron which is emitted from the nucleus of an atom undergoing radioactive decay. A fast-moving electron is a beta particle. So I've signified there. Look at that. That little bit right there. Man, that's a fast-moving thing right there. And there's my electron. So beta decay occurs when a neutron changes into a proton and an electron. So what we have happening is a neutron is converted to a proton, and then this fast-moving electron is given off. And that electron is a beta particle. So stop and think. When we're talking about A and Z, when we're talking about A and Z, okay, the nucleus has one less neutron, but it has one extra proton. So the number of neutrons goes down by 1. The number of protons increases by 1 when I'm dealing with beta decay. So, what happens in terms of A and Z? The atomic number Z increases by 1. Remember, I just said we have changed a neutron into a proton. So, my number of protons, which is my atomic number, increases by 1. The letter A, okay, the number of nucleoids stays the same. Why does that stay the same? Okay, we just said, Jaden, what is a nucleoid? What are they? You just told me a couple minutes ago. Okay, what's in the nucleus, which is? Neutrons and protons. Okay, so what's happening if you look back up here? We have one less neutron, but one more proton. So is that going to change my number for A? No. Okay, it's going to keep the A the same number. What's going to be changing is my Z. So when I write out my equation, okay, and I look at this, I'm taking my polonium here. I'm going to change one of these neutrons into a proton. So my 218 is going to stay the same. My 84 is going to increase by 1. Okay? It's going to increase by 1. So what is element number 85? What's element number 85, Jillian? I know the number. I just said it's 85. What element is 85? Aspartame. So, I'm going to have aspartame produced. Once again, look, my A is the same, 218. My Z is different. My number of protons is different. And then I also have given off this beta particle. Okay? That little B with the -1 is signaling that this is an electron, and that is the beta particle, beta decay. So when I write out my equation, here is the equation that you need to copy into your notes for beta decay. So I'll give you a second to do so. Yeah, Jaden?
That's what you're making it in the notes, in the video notes, or is that something else?
That's something else. I would write this down. So once again, looking at this, right here is my important part, because it shows how my unstable nuclei is converted into my more stable nuclei. And how do I do that? Well, A stays the same, and I add 1 to Z. So by looking at that, I know that Z is number of protons. So in beta decay, what is actually happening is a neutron is changing into a proton, and then I have this beta particle given off. So the one we just did, okay, the polonium to the adenine gives me the 84 plus 1 is 85. The 218 stays the same. So let's look. Okay? If I look right here, I have thorium here again. Thorium-234. It is undergoing beta decay because I can see my beta particle given off right here. So I know that what has to happen here is it's got to be Z plus 1. Madison, what's 90 plus 1? 91. What's element number 91? proactium. So we're going to see that we have made proactium 234. Our Z changed by 1. It went up by 1. Our A stayed the same. Now let's go through and let's look at this. Math-wise, okay, is my Z 91 minus 1 gives me 90. So it's still the same on both sides when I do my math. Okay, 234 plus 0 is still 234. So when we take the sum of the ones on the right side of the arrow, it's still equaling the total on the left side. Now let's go the other way. Okay, let's go the other way. I'm looking at this once again. How am I going to determine, Loudon, how am I going to determine what element I have right here? X. I'm going to take 1 away from this one. Okay, so I'm going to take 82 minus 1 to give me 81. What is element number 81? Thallium. Okay, so what I'm going to have here is 81. I'm going to have of my X is going to be TL. What's my A going to be? 210, because remember, the A doesn't change in beta decay. So I'm going to have 210, 81, thallium. Good. Our third type of radioactive decay is electron capture. Now, in electron capture, it's almost the opposite of beta emission or beta decay. Now, in beta decay, that electron was given off, a high energy electron. Well, in electron capture, that electron is going to be captured, so to speak, by the nucleus of the unstable radioisotope. So, the capture of an electron allows a proton to turn into a neutron. So try to picture out what's going to be happening in my equation. A proton is turning into a neutron. What's going to happen in that equation? Well, okay, here is our equation for electron capture. Go ahead and copy that down. Make sure you got it somewhere. But a proton is changing into a neutron. So my Z number is going to be going down by 1. Okay. My Z number is going to be decreasing. My A number, once again, it's going to stay the same because I've taken a proton and made it into a neutron. So the Z number will stay the same. The one that's going to be changing is, or excuse me, the A number will stay the same. The one's going to be changing is the Z number, the bottom one there. So, right here, what did we say that was, Jillian? Astenine? Okay. Astenine right here. If it is undergoing electron capture, we're going to have that electron there. That electron that is being captured. So my 85 is going to go down to 84, which is going to be polonium. So this is basically, when I look at this, isn't this basically the opposite of what was occurring in beta decay? Okay, so it's kind of the opposite of what happened there in my beta decay. Now notice where this electron is. It's on the left side of the arrow, isn't it? So that's one way that's going to help you out to determine where electron capture is, because that electron's on the left side of the arrow. Okay? This right here, just to give you a little heads up too, I've seen where I had that beta particle, that 1 over or 0 over minus 1 with the little b sign. I've seen that written out as this right here, as this electron like this. So just be aware, because I think we're going to see when we do our nuclear decay gizmo, you're going to see that the gizmo people write out the beta decay as that E instead of that B that I had. So basically, once again, reviewing. During electron capture, we have the capture of a negative particle forming a neutron from a proton. The atomic number decreases by 1. The atomic mass, the atomic number stays the same. The mass number. Dang it, I'll get it one of these times. Atomic number decreases. The number of nucleons, let's just say it like that. Number of nucleons stays the same. So if we look at electron capture, you've already written down this equation, right? Okay. So let's look and actually do one. Okay. Right here. I have argon 37. What, Olivia, what is going to be my Y here? It is going to be chlorine, because 18 minus 1 is 17, right? Element number 17 is chlorine. What's my top number going to be, Olivia? 37. Good. So the electron capture with argon 37 is going to give me the more stable nuclei of chlorine 37. Can I write the equation for the electron capture of nickel 59? Now, see, this is a little bit different than what we have been doing, but it's not. Okay? The little bit different is just, they just tell me that I have nickel 59. Now, remember, that 59 is the number of protons and neutrons. So that's my top number. That's my A. So I'm going to write nickel, Ni. My top number is going to be 59. What's the bottom number going to be? What is it, Zoe? 28. Why is it 28? Because that's the atomic number of nickel. So I have nickel 59 right there. I don't have that 28 in there. Can I put that 28 in there? I could. Now, with electron capture, what is going to happen? I am bringing in that electron, right? So 28 minus 1 is going to give me 27. Element number 27 is cobalt. So I'm forming cobalt 59 when I have that electron capture. Now it says find the missing starting material. Okay. 6. I have carbon right here. So what's this got to be here? What's that got to be there? What number right here for Z? 7. What's element number 7? Nitrogen. So I'm going to have nitrogen 14. Positron emission. This is the last one we're going to talk about today. Positron emission. A positron is like an electron, but it has a positive charge. Notice that this is not a blue one, it's a green one now. So during positron emission, a proton changes into a neutron, and the excess positive charge is emitted. So here is my equation for positron emission. Make sure you get this copied down into your notes. A proton is changing into a neutron. So my atomic number is going to decrease by 1. Okay, my number of nucleoids is not going to change because the proton changes to a neutron. Notice, though, if you look at this, okay, if you look at this, that is my positron. Okay, it's like an electron, but it has a positive charge. So if I have the positron emission, it's going to tell me my 85 is going to lose one of those protons. So 85 is going to turn to 84. The 218 is going to stay the same. Element number 84, once again, is polonium. So I'm going to have polonium and this positron. So the atomic number decreases by 1. The mass number stays the same. So what is Y here? What is Y? Four, so it's going to be what element? Beryllium. So it's going to be beryllium 8. Okay. Write the equation for the positron emission of oxygen 16. So oxygen 16 is going to be oxygen 16 over 8. Okay. What's 8 minus 1? 7, right? So that's going to give me nitrogen 16. Okay. We're going to end it right there, folks. We'll continue on with this stuff.